Hey guys, this is going to be a video series on quantum chemistry. This is going to be the first video in the series, and it's going to begin with a math review, and we're going to start with three-dimensional vector algebra. So maybe you've taken a physical chemistry class. The second semester of physical chemistry usually deals with quantum mechanics and its application to physical chemistry, whereas the first semester usually deals with thermodynamics and kinetics, but it doesn't really go that deep in terms of mathematics. So this is a really good place to start if you want to look at some more advanced topics in physical chemistry, in particular in quantum chemistry, or if you want to do undergraduate research, or maybe you're even a graduate student that hasn't had a course in linear algebra, or you need a refresher in linear algebra. This is a very good place to start. And we're going to start with the basics of three-dimensional vector algebra. And so we're going to start by talking about basis vectors. So we can say that if we're using the components AI with respect to a set of three mutually perpendicular unit vectors, and then in brackets we have E subscript I, and when we write the brackets with E subscript I in between the brackets, then that's going to be our unit vectors, and AI is going to be representing the components of our vector. We can represent, and I should say, okay, AI, instead of saying represents the components, let's just say that's what we're going to write for the components. Because in more formal terms, we're going to be able to represent a vector. We can say we can represent a vector A using the unit vectors EI and the components AI. So this is written here in our first equation. We have that A is equal to, and we're talking about, this is for three dimensions, okay? So A is equal to E1 A1 plus E2 A2 plus E3 A3, or we can say in general the sum of all EI's and all AI's. So like say I is from like 1 to 2, so it's like E1 A1 plus E2 A2. Okay, so that's in like two dimensions. Okay, so you can extend it, but we're going to be dealing with, you can extend it where you can even subtract from it, but we're going to be dealing with three dimensions in this video. So if you remember from linear algebra, we have our terms completeness and uniqueness, and we can say in this case what we want to bring those two concepts up for is we want to say that if we have vectors that form a basis, we can write that basis, or we can write the we can write the 3D vector as a linear combination of the basis vectors. So it's basically what we're saying in the first equation is that A is some vector, and then we have E subscript I as the basis vectors, and then we have the components AI. Okay, and in terms of uniqueness, we can say that the basis is not unique. So we could have we could have just chosen other basis vectors. So we could have said A is equal to epsilon 1 A prime 1, and then the same for epsilon 2 A prime 2, epsilon 3 A prime 3, and then you can write it in general using summation notation. So this is a lot of simple stuff, but it's important to get the definitions down. So we can say, given a basis, a vector is completely specified by its three components with respect to that basis. So, for example, with reference to that, we can say, all right, we've got this vector A, and then we have entries A1, A2, and A3 in a column vector, and it's in the basis E1. And then say we have a vector A prime, and then we have entries A prime 1, A prime 2, A prime 3, and then it's in the basis epsilon I. So we have different basis vectors, okay? And then if we look at multiplication for these vectors, we can say that A dot B is equal to A1 B1 plus A2 B2. And then in general, you can say that it's AI dot BI, okay? And then you write it in summation notation. So say you had like 4 entries, then you would have like A4 B4, but we just have 3 here. Okay. And then we have another definition here for if you take the inner product of A with itself, vector A with itself. Okay, now let's evaluate the scalar product A dot B. So we can say that, remember, the vector A we can write in terms of the basis vectors and the components. So we can say we are dealing with the sum of all the I values of EI and AI, okay? And then for B, we're just going to define it the exact same way. It's just another vector, and we're going to give it the index j, okay? So multiplying that out, we have A dot B. These two vectors, we're multiplying them together. We have the summation over the indices of I and j, and then we write EI dot EJ times AI BJ. Okay? And then if we say then that for EI dot EJ, so for the first part after the summation indices, so after the summation over I and j, right? Directly to the right of the equal sign, you see EI dot EJ. So we can write delta, that's equal to delta ij, or delta ji, and that's the Kronecker delta, and that's basically telling us, okay, if I and j are equal to each other, then that equals 1. But if they're not equal, if I and j aren't equal, then that equals 0. Okay, so A dot B, if we have the same, if I is equal to j, then that's just 1. Okay, then the part of it that is EI dot EJ, that's just 1, and it equals AI BJ. Okay, but if they're all equal to each other, it would be like writing AI BI. That's what that is equal to. Otherwise, it's 0. Otherwise, the whole thing is 0. All right, so this implies that the basis vectors we've chosen are mutually perpendicular, or we can say orthogonal, and they have unit length. Okay, so they're normalized. All right, because if we take A dot B and they have the same, like let's say that we have AI and BI, all right, they're equal. Basically, I and J are equal. Then we're gonna get 1. Okay, and then otherwise it's 0. That tells us that we have an orthonormality relation. Okay, so this is probably stuff that's going to start coming back to you from your PChem 2. All right, or maybe you're a physics major and you're trying to get into quantum chemistry. This is probably mostly review that you've probably learned formally, but the people that are in chemistry probably haven't learned. They probably haven't learned this that formally. Okay, so we can say. After that, we can say, given a vector A, you can find its complement along EJ by taking the scalar product of A with EJ and using this orthonormality relation. All right, so now we're going to actually write this out. So we want to find the complement. Okay, so we're going to find the complement along EJ, okay, which is just AJ, okay, A subscript J. So we have EJ dot A is equal to, and then we're going to write a summation with index I, and we're going to write EJ dot EI AI. Okay, and remember we said that EJ dot EI can either be 1 if I and J are equal, or if they're not equal, then it's 0. Okay, so in other words, we can write delta IJ, which is the Kronecker delta, and that's our orthonormality relation that's written out formally, so we can put it in an equation. And so if it's not 0, then it's 1. So we're just going to say, okay, these two are equal to each other, and so we end up getting AJ. And we can rewrite A as the sum of EI times EI dot A, okay? And the sum of EI times EI is just 1, okay? So that whole thing is just going to equal the vector A. Okay, and then we have this. I think on the screen it says unit dyad. It's the unit dyadic here, and the unit dyadic is just that 1 is equal to the sum with the index I of EI times EI. Okay, that's just going to equal 1. So that's going to be something we're going to use later, and it ties into the completeness relation for the basis EI, and it states that any vector A can be written as a linear combination of the basis vectors, and then in brackets we're writing EI. And we already said that at the beginning. Okay, so this is just us stating this out formally. Okay, now we're moving on to linear operators. We can define an operator O, capital O, as an entity which, when acting on a vector, say a vector A, converts it into another vector. So we can say converts a vector A into a vector B, okay? So the operator is linear if O, and then in parentheses we have X times A plus Y times B, and the parentheses is equal to X O, and then you write the vector A after the O because it's acting on that vector, and then you add that to Y, and then the capital O, and then the vector B to the right of O because it's acting, the operator O is acting on the vector B. Okay, and so we can write the vector O E subscript I as a linear combination of the basis vectors of E subscript I. Okay, and we can write that formally. We can say O acting on the basis vector E subscript I, or the basis vectors E subscript I, is equal to summation with an index of j. And remember, with the definition of an operator, we're taking this operator O and it's acting on some vector. So in this case, the basis vector is EI, okay? And it's converting it into another vector, all right? So now we have a different index, all right? We have the index j because we now have another vector, okay? And so we're going to say O E subscript I is equal to, and then with summation notation, we're writing from the index j is equal to 1 to 3, because we're in 3 dimensions, and we have EJ multiplied by this thing OJI. Okay, so what is OJI? OJI is the component of the vector OEI along EJ. Okay, so I'm going to say that again. OJI is the component of the vector O E subscript I along EJ. And remember how we found the component of A along EJ. This is similar, but we can write O in a matrix representation. So we're gonna get to that in a second. But we can say, for instance, let's say we had O acting on E1. Okay, so then we'd write with the summation from J of 1 to 3, we would say EJ, and then we're multiplying that EJ by OJ1. Okay, so if we write O in the matrix form, then these I and J just correspond to the rows and columns. Okay, so for example, we have O, I, and J. If I is 1 and J is 1, then that's just O11. Okay, so that's the entry in the first row and the first column of the matrix representation of O. Or we can write this out. We can say that OE1, and then we look at the corresponding parts of the matrix where we're getting these complements from. So we say OE1 is equal to E1, so that's the basis vector E1 multiplied by the complement of the matrix representation complement of the operator. So we're saying E1 multiplied by O11 plus E2 O21, and look where that comes from. That's the second entry in the first row of the matrix representation of the operator. And we're talking about operators in general, so you're going to remember this from your PChem class. We have a bunch of different quantum operators. But okay, so E2 O21 plus E3 O31. Okay, and we can say, again, we're saying that O is the matrix representation of the operator O in the basis EI. And I just gave one example. That's just if we have OE1. Okay, so it's like I said, we're looking at the complement of the vector EI along EJ, so we're just saying, okay, we could say, what if we're looking at, instead of E1, we're looking at E2? Okay, well then it's just it's these basis vectors, and then instead of multiplying the basis vectors by the components in the first column, we just look at the second column. So it would be like OE2, and then it'd be E1 multiplied by O12. Okay, so that's the those are the basics for dealing with the linear operators. Okay, so I think that's enough for one video. That's going to be our intro to three-dimensional vector algebra. for quantum chemistry. And I think what we're going to do next is we're going to do an example problem because I've basically just given a bunch of definitions. So we're going to do example problems next so you can see this stuff in action.